Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about program control instructions. At the end of this video, the student can gain knowledge regarding what are the various varieties of program control instructions, how the execution sequence of program can be altered with these program control instructions conditionally and unconditionally, how to apply these instructions while development of the assembly language program. The basic agenda of this video is introduction, program control instructions, examples, what are subroutines, and how stack can be organized during execution of subroutines. So computer can provide variety of instructions. So it can have a rich set of instructions to give flexibility to carry out various tasks. The intended functionality should has to be supplied with the help of these instructions available in the instruction set by the user. Instruction set is different from one computer to another computer. The basic set of operations generally involve the data transfer instructions which facilitate the transfer of data from between registers, between memory and IO devices without changing the content. The next category of instructions generally data manipulation instructions. These instructions provide the computational capability to the system. The third category of instructions are program control instructions. The program control instructions generally used to alter the sequence of execution of the program. The data transfer instructions facilitates the shifting of data between registers or from memory to register or from register to IO. General instructions under these data transfer instructions are load, store, exchange, in, out. All these instructions are generally the data transfer instructions. The next category of instructions are the data manipulation instructions. The data manipulation instructions facilitates the computational as well as decision making capability. There are three categories of instructions under data manipulation instructions. They are arithmetic instructions, So here the calculations can has to be done. The processing can be done by the computer with the help of these arithmetic instructions. The arithmetic instructions generally involves add, sub, mul, div to facilitate various arithmetic operations. Next category under data manipulation instructions are the logical or bit manipulation instructions. The bit manipulation instruction facilitates to operate on a single bit stored in the resistor. These instructions provide generally the decision making capability to the computer. The general instructions that involved under this category are and, or, exclusive or, etc. The next category of data manipulation instructions are shift instructions. The shift instructions are generally used for serial data transmission. There are three types of shifts are available: logical shift, arithmetic shift, circular shift. Under these two varieties, again two types are there: left shift operation and right shift operation. To support these operations, the mnemonics that can be used are ROR, ROL, SHL, SHR, etc. Now, the third category of instructions are the program control instructions. Generally, the program can be executed one after another in a sequence, the instructions. A program can be considered as collection of instructions that can be uh, written to achieve a specific objective. During execution, the instructions can be fetched and can be executed in a sequence one after another. If user need to alter the program execution sequence, then the program control instructions can be used. So the three categories of instructions are data transfer instructions, move data from one place in computer to another without changing the data content. So there is no change or effect of the content. The transfer of data can be taken place. So the common transfer involves processor register to memory, processor registers to IO, and processor registers themselves. Next variety of instructions are data manipulation instructions. These are provided to facilitate computational capabilities for the computer. Three types of instructions are there: arithmetic instructions, logical or bit manipulation instructions, shift instructions. Next variety is the program control instructions. Program control instructions specify the conditions for altering the content of the PC. PC is the program counter register which hold the address of the next instruction that is going to be executed by the CPU. So here the next address can be stored in PC so that the altering of the PC content can change the execution sequence of the program. So by using these program control instructions, specify the conditions for altering the content of the PC. While data transfer and manipulation instructions specify conditions for data processing or data transfer. The change in the value of the PC as a result execution of the program control instruction causes a break in the sequence of instruction execution. So, the sequence of flow of execution of the program can be suspended with the help of these program control instructions. These instructions provide control over the flow of program execution and capability for branching to different program segments. With the help of these mnemonics available under program control instructions, the user can easily switch from one segment of the program to another segment of the program. Generally available program control instructions are branch instruction, jump, skip next instruction, call procedure instruction, return from procedure instruction, compare, test. To support the branch instruction, the general mnemonic used is BR. To jump from one segment of the program to the another segment, JMP. To skip to the next instruction, SKP. To call the specified procedure, CALL call. To return from a procedure, RET return. To compare, CMP instruction. To test a condition, TEST. So these are the general mnemonics used for the program control instructions. How the branch mnemonic can be worked. Branch is one address instruction. When executed, the branch instruction causes a transfer of the value of address into the PC. So while during execution, if branch statement is occurred, then the specified label associated with the branch, the program sequence can be altered. From that label onwards, the execution of the instructions in a sequence can be continued. So this way the branch instruction can be used. Jump is branch and jump instructions are used interchangeably to mean the same thing. Jump and branch are generally the unconditional branching statements. So without checking any condition, the altering the sequence of execution of the program can be done with the help of branch and jump. Skip instruction will skip to the next instruction. Whenever a subroutine is encountered, the subroutines are the small piece of code that can be called when is needed by the main program. The frequently or repeatedly used code segments generally placed in the procedures in order to provide reusability of the code. So here, call instruction can call the specified subroutine. Whenever a subroutine call is encountered, the flow of sequence of program execution can be suspended. And what is the name, subroutine name or the procedure name specified with the call statement, the program can switch to that procedure and start execution of the subroutine instructions one after another in a sequence until it finds the return statement. Whenever return statement is encountered, the control flow can alter or switch to the main program and continue the execution of the main program. So call is used to call a subroutine. Return is used to return the control from the subroutine. Next instruction is the compare. So comparison has to be performed between the two operands, but the result of the operation is not returned. However, certain status bit conditions are set as a result of the operation. So we'll discuss about what are the status register bits. Next is test. Performs a logical and of two operands and updates certain status bits without returning to the result. So these are the list of program control instructions available. What are the status register bits? In order to perform conditional branching, these status register bits are useful. So these are used for conditional code bits or the flag bits. The bits are set or cleared as a result of an operation performed in the ALU. Generally, 4 flags are available in the PSW register, program status word. The 4 flag bits, status flag bits are denoted with C. C is representing the carry. So, it is set to 1 if a carry out of the ALU is 1. While performing the binary arithmetic, so binary addition, if 2 ones are stored in the register, while adding this, the sum can be 0 and with a carry. If it are a carry is resulted in the ALU, the C bit has to be set to 1 in the status register PSW. Next is in order to represent the sign of the register value. The sign bit is used to denote whether the stored value is positive or negative. If sign bit is 1, the stored value is the negative value. The MSB bit of the ALU output is the sign bit. Next is the Z. Z is representing the 0. Set to 1 if ALU output is all zeros. When the result of arithmetic logical unit operation is 0, then the Z bit can be set to 1 in PSW. Next is B, overflow. Set to 1 if there is an overflow. For example, in a binary arithmetic, 2 operands are considered and if the result is producing extra bit, these 2 operands are of 4 bit size, and if after performing the arithmetic operations, if the result is generating the 5 bit, This extra bit can be treated as the overflow bit. If it can be set to 1 if there is an overflow. If the result is 4 bits only, the V bit can has to be set to 0. So depending upon the ALU operations, these flag bits can be set to 1 or 0. So 4 flag bits are used: the carry, sign bit C, sign bit S, 0 bit Z, overflow bit V. So these 4 flag bits can be stored in the resistor. So here the VZSC. So here the test can has to be checked out the value of these flags. Accordingly, the branching or jumping can has to be take place. But the jump and branch are the unconditional. No test can be performed. So here, if it want to make the conditional, then based on these flag values, the alteration of the program execution sequence can be considered. So here, what are the status bit conditions? C is the first status flag, that is the carry. If end C8 is equal to 1, then the carry bit has to be set to 0. S is the sign bit. Highest order bit F7 is equal to 1. Then F7 is equal to 0. Even the 0, output of ALU contains all zeros. Otherwise it can be 1. Then V bit overflow, XOR of last two carries 1. Otherwise it can be set to 0. So these are the status bit conditions. How to apply these program control instructions? Branch and the address are the label that can be specified. Then the specific address, the program execution sequence can be altered. JMP label, whatever label specified. So again label that is presented where in the program segment, there the control flow can be altered. Escape for the skip, and in order to call a procedure, then call function 1, and while returning to the procedure return, comparing the register value whether it contains 0, the AND operation can be performed, testing the two values R1 value and R2 value with the AND logical operation. So like this, the program control statements can be used in the assembly language. How the conditional branching can be performed? Generally, these condition checking can be done with the status bit flags. So the first category are the branch conditions when testing the status bit flags. So the first instruction is the BZ. BZ means branch if 0. The 0 Z flag of the PSW can be tested. If it all 1, then only the alteration of the program sequence can be done. Next is BNZ, branch if not 0. That means when Z consists of 0 value, the branch operation can take place. Next is BC, branch if carry. When the carry flag is equal to 1, then branch operation can be performed. Next is BNC, branch if no carry. When carry flag is equal to 0, then branch can be occurred. Next is BP, branch if plus. Depending upon the sign bit, if sign bit consists of 0, the positive numbers can be stored. So if the positive numbers stored, then only the branch can be take place. Next is BM, branch if minus. So if S is equal to 1, then the branch can be taken place. Next, depending upon the overflow flag, BV, branch if overflow when V bit is set as 1. BNV, branch if no overflow when V bit is set to 0. So depending upon the status flag checking condition, the condition has to be verified. Based on that status flag values, the branch operation or program execution sequence alteration can be performed. The next set of instructions are depending upon the values stored in the operands or the registers. So, two operands A, B are involved. So, the comparison operation can be performed with the A minus B. So, while comparing the values stored in the two registers, the condition based on the checking of the condition, if the condition satisfied, then only the branching can be takes place. The first instruction on the unsigned compare conditions, BHI, branch if higher. How the higher can be checked is A greater than B. BHE, branch if higher or equal, A greater than or equal to B. So, while how you are using in the high level languages, the relational operators, here these statements can be worked like that only. So, BLO, branch if lower, that means A less than B, the branch can be take place. BLOE, branch if lower or equal to, that means A is less than or equal to B, the branch operation can be performed. Next is BE, branch if equal. If A is equal to B, the branch operation can be executed. Next, BNE, branch if not equal. When A not equal to B, the branch of the branching of the or alteration of the program sequence control can be executed. So these are the unsigned compare conditions, but how these operations can be executed with signed compare conditions. So BGT, branch if greater than A greater than B. BGE, branch if greater or equal to. So A greater than or equal to B, branching can be performed. BLT, branch if less than A is less than B, the branch operation can take place. BLE, branch if less or equal, A is less than or equal to B, branch operation can be take place. BE and BNE can be used to check for equality and not equality conditions respectively. If these conditions are satisfied, then only the branch operation can be performed. So these are the various mnemonics that can be used in case of conditional branching. So the tested condition is satisfied, then only the branching operation can be performed. So these testing can be performed by using the flags status registers or status register flags, or by comparing the values stored, the unsigned and signed comparison of the register values. How these program control instructions can be applied. So here we incrementing the EDX register and CMP EDX, 10. That means the EDX value when reached the value 10, the comparison can be performed. Then only jump operation can be performed to the LP1. So JLE means jump less than or equal to 10. Then the conditional, the transfer of the program control can be performed by comparing the EDX value whether it is less than or equal to 10. The second example is adding or incrementing the AX value by 1, and we are, after the second instruction can add the AX value and the BX value, store the sum in the BX value. Next, shift left CX by 1. Next, jump L20. So repeats the statement. So here L20 has to be the address can be used to alter the program control. So like this, the program control instructions can be used in the assembly language programs. Not only by using program control instruction, while execution of interrupts also, the program execution sequence can be altered. So what is an interrupt is, an interrupt is in the architecture is a signal. Okay, it is a signal that requests the processor to suspend its current execution of the program and service the occurred interrupt. So, to service the interrupt, the processor executes the corresponding interrupt service routine. Each interrupt that is raised has associated with a ISR, interrupt service routine. When this interrupt is raised, the computer can stop the current program execution and can transfer the control to the ISR and start executing the ISR. So after the execution of the interrupt service routine, the processor resumes the execution of the suspended program. So in the similar way, the interrupts can be serviced. So this is the user program. User program can have the number of instructions. Those can be executed one after another in a sequence. So if at all an interrupt is occurred here, interrupt occurs here, then the control can be transferred to the ISR. So this is the interrupt service routine. So the program or the instructions stored in the interrupt service routine can be executed. At the end or completion of these instructions can return to the user program and starts resuming its operation of execution of the user program. In this way, the interrupts can be serviced. So, during execution of the interrupt cycle, at the end of the instruction cycle, the occurrence of interrupts can be checked. So, here in the instruction cycle, generally fetching the instruction, next executing the instruction. So, fetch and decode operation can be performed in the fetch cycle, and getting the respective effective address of the operand and execution of the instruction can be done in the execution instruction. If at all the execution of instruction completed without interrupt, then stop the program execution. So, if at all an interrupt is enabled, then check for the interrupt. So, it has to alter the control to the ISR and service the ISR. After completion of its execution, again from the next instruction onwards, the instruction cycle can be commenced. In this way, the interrupt cycle at the completion of each instruction, check for the interrupt. If it all raised, it can be serviced. How the system can recognize that an interrupt is raised. So, depending upon the R value, R is the flag. Depending upon the R flip-flop value, whether it is 0 or 1, the system can decide either to execute the instruction cycle or the interrupt cycle. If at all R is equal to 1, the interrupt cycle can be commenced and store the return address in the location of memory location 0, the PC address, and branch to the location and increment the PC value, and IEN is 0 or is 0 to indicate that it is servicing a interrupt. In case of instruction cycle also, during input-output operations, interrupt can be generated. So, this can be identified with the IEN, interrupt enabled. And in case of it is a input device interrupt, FGI can be activated. In case of it is a output device, then FGO can be activated. So, during fetch and decode instruction, and if IEN is enabled, which indicates that IO interrupt can be enabled, and depending upon that is indicated for the input device, FGI is equal to 1. If at all it is related to the output device, FGO can be 1. So, this can be serviced by setting the R is equal to 1 to indicate that interrupt is raised. So, after completion of the ISR, then it has to move to the user program to continue its execution. In this way, the interrupts can be executed by altering the program control sequence. Not only the interrupts, in case of subroutines also, the program flow control can be altered. The subroutines can be procedures or functions. A set of instructions which are used repeatedly in the program can be referred as a subroutine. So, the subroutines generally contains a small piece of program code which can be repeatedly used or can be called by the main program. So, through these subroutines, the reusability of the code can be increased. Only one copy of this instruction is stored in the memory. When a subroutine is required, it can be called many times during the execution of a particular program. So, as and when required by the functionality of the subroutine, it can be called by the main program. A call subroutine instruction calls the subroutine. The mnemonic that can be used to activate the subroutine is CALL call. The content of PC must be saved by the call subroutine instruction to make a correct return to the calling program. After completion of the execution of the procedure, again it has to return back to the main program to resume its execution correctly. So, to facilitate this, the PC address can be stored in the stack. Stack data structure is most efficient way to store the return addresses of the subroutine. How the subroutine can be executed. So, the instructions can be executed one after another in a sequence. When there is a call, mnemonic can be observed in the program to make a call to the subroutine instruction. Whatever the name, procedure name specified in the calls instruction, to that subroutine, the program control can be altered. That subroutine can be executed one after another, and whenever a return, the end of the subroutine is encountered, the program flow can be altered to the next instruction in the user program in order to resume its main program execution. So, in this way, the program flow can be altered in case of subroutines. So, this is how the flow of execution of the subroutine can be taken place. So, here main program, whenever a procedure call occurs, it has to shift or alter to the procedure instruction, execution of the subroutine instructions until it find the return instruction. Whenever a return instruction occurred, it has to move to the again main program and continuing its execution. So, whenever a procedure call is encountered, the PC value can be shifted to the stack. So, it can be pushed to the stack, and whenever a return instruction is encountered, the value can be popped from the stack in order to resume the main program execution. So, how the call procedure can be used? So, here call M1 move AX, 2. Whenever a call statement encountered, so it can alter and move the control to the M1 program procedure. So, here M1 procedure, moving operation, data transfer operation, the 5 value can be moved to the BX register and return. When it encounters the return, the next instruction of the main program can be executed. 2 value can be moved to AX and return. So, like that, the call can be used to make a procedure call, and return is used in order to return from the subroutine. Nested subroutines. Subroutine nesting is a common phenomena in the high level or any programming languages. A subroutine is called within another subroutine, then it can be generally treated as a nested subroutine. Subroutine nesting is a common programming practice in which one subroutine can call the another subroutine. Subroutine 1 calls the subroutine 2. The return address of the subroutine 2 should be saved in the stack. So if link resistor stores return address of the subroutine 1, this will be by return address of the subroutine 2. In order to perform correct return operations, the return address can be pushed to the stack, as the last subroutine called is the first one to be returned. So stack follows the LIFO phenomena to organize the elements. So the stack data structure is the most efficient way to store the return addresses of the subroutines in case of the nested subroutines. How the nested subroutines can be called? So here subroutine 1 calls the subroutine 2. So here the return address of the subroutine 1 can be saved in the stack. Whenever subroutine 2 calls the subroutine 3, the return address of the subroutine 2 can be moved to the stack. And the return address of the subroutine 3 can be pushed to the stack. And whenever a return statement encountered in the subroutine 3, the address can be popped and resumed to the subroutine 2. Again, the return statement that can be encountered in the subroutine 2 can make a move or shift to the subroutine 1 until the return statement find in the subroutine 1. In this way, the execution of the nested subroutines can be take place. Now, with an example, we will discuss about how the return addresses can be pushed to the stack and how they can be retrieved during the return of the subroutine. So why the stack is most effective data structure to store the return addresses means the stack is using the LIFO technique, last in first out. So this is the best or efficient way of storing the return addresses of the subroutine. The resistor used to store addresses of the topmost element of the stack is called the stack pointer SP. And two operations can be possible to perform on the stack data structure, that is push and pop. Push is used to insert an element in the stack. Pop is used to retrieve an element from the stack. So with an example how nested subroutines can be used, nested procedure calls can be made in the program. This is the main memory. So this is the 00 address. The main program is starting its execution in a sequence, and there encounters the call 500. So that is the address. The procedure call is encountered at a address of 100. So the next PC can hold the address of the next instruction. So the PC value can be 101. So this 101 can be pushed to the stack. Then immediately the control can be transferred to the subroutine 1 and starts executing the subroutine 1 instructions in a sequence one after the another. In the subroutine 1, there is another procedure call. So here call 900 can be occurred at 600. The PC value can be 601. So before moving to the procedure subroutine 2, the PC value can be shifted to the stack. So 601 can be pushed to the stack. So here this is the stack pointer position. Next here call 900. 900 address can be altered and the subroutine 2 starts get execution. So it is executing and at the last it can find the return. Whenever a return is encountered, it has to fetch the return address from the stack. The top of the stack is 601. So the 601 location has to be retrieved from the stack, so that from 950 it has to move to 601 and resume the operation of the subroutine 1 and start execution of the subroutine 1. Whenever they encountered a return address, return statement, the return address can be popped from the stack, that is the 101. So it has to shift to the 101 and resume the main program execution and start execution of the main program. In this way, in case of nested subroutine calls, the stack organization can be most efficient way to store the return addresses during the procedure calls. So multiple the nested subroutine, in a subroutine, another subroutine call can be occurred. Those can be effectively managed with the help of stack data structure. So in the program control instructions, how the branching, jumping and calling of procedure can be take place, we discussed. Not only that, by using program control instructions, the change altering of the program sequence can be occurred, but by using the interrupts and also subroutine calls also, the program control can be altered. So these program calls can be effectively managed with the data structure stack, and how this can be efficiently managed with the examples we discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.